Hello and welcome to yet another video where we continue to talk about this important physical quantity in mechanics called momentum. We have defined momentum. We have seen how we calculate momentum by multiplying the mass of the object and its velocity. We have seen how the momentum of a given object changes. We have even calculated the change in momentum. But one thing that we have avoided talking about is what causes the momentum of an object to change. Better still, what causes the velocity of an object to change? Because when the velocity of the object changes, then its momentum changes. I want to take you back to that time when you started talking about forces. And immediately you defined a force as either a push or a pull. By the way, we are going to define a force differently when we look at further details about momentum. But then we defined a force as either a push or a pull. And then we went ahead and stated that the SI units of force is Newton. Again, we are going to define the Newton in this particular lecture. Then we went ahead and listed several effects of a force. You will definitely remember that one of the effects of a force is that it can change the velocity of an object. It can change the direction in which an object is moving, plus many other effects. So, what causes the velocity of an object to change is a force. So today we are going to look at the relationship between force and momentum. And I'm going to start by looking at an object. Supposing you have an object of mass m moving with an initial velocity u, and then over a certain duration of time t, a resultant force F acts on it, changing its velocity to v. What are we talking about? We are talking about this situation here. I have this object. It has mass m. At this instant of time, it's moving in that direction with velocity u. And then after time t, there is a resultant force acting on it for time t, changing its velocity to v. That is the situation that we have. We have an object, m. It may be a car. It may be any other object out there where we can exert an external force. For example, for the car, the external force will be the driving force due to the engine. That driving force due to the engine acts on the car for time t, maybe 10 seconds, changing its velocity from, say, a velocity of 20 meters per second to 25 meters per second. Let's see some of the things that we've talked about. We've talked about its initial momentum, pi, which will be mu. We've talked about its final velocity, its final momentum, its final momentum, which will be p, f, and of course both of them are to the right. This one is to the right, and this one is also to the right. Given that both these momenta are in the same direction, we can easily talk about the change in momentum, which is delta p, which will be p final minus p initial. And I want to remind you here, when you talk about the change in a given physical quantity, we usually get the final magnitude minus the initial magnitude. That is how we get change in a physical quantity. And of course, this one is going to be equal to mv minus mu. You can write this like this. This is change in velocity. V minus u is change in velocity, and we can talk about something like that. So the change in momentum is equals to mass times the change in velocity. Now, At what rate is this momentum changing? At what rate is this momentum changing? We are going to see that momentum, the rate of change of this momentum will be delta P divided by T, which will be equal to M delta V divided by T. And from kinematics, we know that change in velocity divided by time gives us acceleration. So this one will be equal to the mass times the acceleration of the object. It's very simple to see this. Now, at this point, we are going to bring a law that connects this resultant external force that is acting and the rate of change of momentum. And this law states like this. In fact, it's referred to as Newton's second law of motion. Newton's second law of motion. It states like this, that the rate of change of momentum, which we have calculated like this, the rate of change of momentum is directly proportional to the resultant external force acting on that object. And that rate of change of momentum is in the direction of that resultant force. I'm going to repeat that because it is so important. The rate of change of momentum of the object is directly proportional to the resultant external force acting on that object, and it takes place in the direction of the force. So let's write down that law mathematically. So mathematically, that law is written like this. F is directly proportional to the rate of change of momentum, which we have seen is equals to ma. Ma is rate of change of momentum. When we want to remove this proportionality sign, we usually put the equal sign, introduce a constant k, and we have delta P over T, or K MA, where M is in kilograms and A is in meters per second squared. From experiments, K is usually found to be equal to 1. So this law turns out to be F is equal to MA. Let's look at these symbols. F is the resultant force. Again, I have already taught you how to work out a resultant force acting on an object. F is the resultant external force acting on this object. It is the one, when it acts on this object, it makes this object of mass m to accelerate or to have an acceleration a. So this resultant force causes this acceleration. It is not the other way around. It is not the acceleration which causes the force. Understand this because it is so important. Here we are looking at the fact that A, which is acceleration, depends on F. It is a dependent variable. This is an independent variable. The driver could decide to press the accelerator and therefore exert more force on the car. It is independent of the acceleration. So the driver decides, do I want more force or do I want less force? And then we look at the effect of that force on the car. When more force is applied, there will be higher acceleration. So you can see the acceleration is caused by the force. In such a situation, we say the acceleration is dependent on the force. That's the first thing that I want you to identify. M is is the property of this object. Like I said at the very beginning when we were looking at factors affecting momentum of an object, which is mass and velocity, the easiest one to change is always the velocity, because you can make the object to move faster or move slowly, thus affecting its momentum. But its mass, it's not very easy to change. It's not very easy to change the mass of the object. So we are going to look at these two. Now, when I'm still here, acceleration is a vector quantity. Acceleration is a vector quantity. Force is a vector quantity. It is the acceleration which is caused by the force. Rather, I should have said, it is the force which causes the object to accelerate. It is the force which causes the object to accelerate. Therefore, the acceleration will be in the direction of the resultant force. The acceleration will be in the direction of the resultant force. Now at this point, I would like us to define units of force. Before I define units of force, I want to use this equation here, or just this, because it is basically the same thing. F is equal to ma, and we look at the right hand side and we'll see that it is referred to as rate of change of momentum. And this is force. Force is equal to rate of change of momentum. It is equal to change in momentum divided by the time taken for that momentum to change. It's at this point that we can define force. The proper definition is this. Force is defined as a rate of change of momentum. It's just as simple as that. So at this point, we want to forget the earlier definition of force which we have always used, which is either a push or a pull. Of course, it helps us to understand, initially, to understand about forces. But when it comes to defining the force, remember, in physics, when we talk about defining a physical quantity, we want to show how it is related to other physical quantities that we have encountered before. When we say it is a push or a pull, it does not give us an equation which shows how it is related to other physical quantities. But this one, of course, gives us an equation which is associated with the definition. So remember, rate of change of momentum is the definition of force. After that, we're going to say the SI unit of force is Newton. So we want to define the Newton because it has a unique name, and it is the name of a person, and it is a derived unit. It's not that like Kelvin, which is the SI unit of a basic physical quantity. The Newton is a derived unit, so it must be defined. So you're going to say 1 Newton is equal to 1 kilogram times 1 meter per second squared. So when it comes to defining the Newton, 1 Newton, it is the force which is required to give a mass of 1 kg, an acceleration of 1 meter per second squared. The Newton is the force that gives a mass of 1 kg, an acceleration of 1 meter per second squared. So understand, we define the force, or we define force as a rate of change of momentum. After that, we state that the SI unit of force is Newton, and then define the Newton, because like I've said, it has a unique name. It is the name of a person, and so we want to define it. Just like we defined the physical quantity, we want to define the Newton. So let's put a few things together. We have defined momentum, seen how momentum can be calculated. We have calculated change in momentum, and then we have asked ourselves, what makes the momentum of an object to change? Then, in getting that which causes the momentum of an object to change, we looked at rate of change of momentum and adapted Newton's second law, which relates rate of change of momentum and force. And we say that the rate of change of momentum of an object is directly proportional to the resultant external force acting on the object and takes place in the direction of the force, or it takes place in its own direction. When you see that word, it means it takes place in the direction of that resultant force. After that, we defined force as rate of change of momentum, stated the SI unit of force as Newton, and then we have defined the Newton, that is 1 Newton. In the next video, we are going to see more applications of F is equal to ma. See you in the next lecture.